In this video, we'll be talking about universal gravitational energy. So what is gravitational potential energy? So we remember that work is equal to force times displacement. So then we're going to use the force of gravity. So what is Fg? So Fg is equal to G times m1 times m2 divided by r squared. So now we plug in F into work. But the problem is that F is not constant for each distance. So how can we need to solve this iteratively for every little change. So how can we do this? We have to use calc. So for the force F, the work done along a path is equal to the integral of F vector times D times R vector. And we also know that a force is conservative if work it does only depends on starting and ending point. So not the path. So therefore, for these conservative forces, we define the scalar function u of the vector of r, which is potential energy, so that delta u is going to be equal to negative work. So that's going to be delta u is equal to negative integral of the vector of F times D times the vector of R. And then we're going to plug in, and because the force is attractive, we're going to use negative G m r squared times dr. And basically, gravity is just the attraction between forces. It's basically the attraction between you when you're feeling gravity. It's when you're feeling the attraction between Earth and you. It's pulling you down. So u of r is just equal to the integral of G times m divided by r squared times dr, and then ur is equal to G m times m integral of r negative 2 times dr, and then u of r is just going to equal to G times m lowercase m times negative 1 over r plus c by using the power rule. And then we have u of r is going to equal to negative G m times m divided by r plus c. So now that we have this, we know that in gravity, we define potential energy to be 0 at infinite separation. So that's going to be, we're going to plug in r is equal to infinity. So u of infinity is equal to 0. So now we find the limit. Basically, we just find as r approaches 0, we have negative G m times m divided by r approaches 0. So we have that UGR is equal to negative GM times m divided by r, and the constant is equal to 0. So now we can do some practice with potential energy. So let's say that the moon stops orbiting Earth and starts to fall in. Okay, and then the radius of the average lunar orbit is going to be equal to R is equal to 3.8 E5 kilometers, and then the mass of the Earth is going to equal to 5.97 E times 24 kilograms, and mass of the moon is going to equal to 7.5 E 22 kilograms. So our question is A, how much energy does the moon have? And the answer for that is going to be, and also, actually, let's write down B. What would its speed relative to the Earth be when it collides? And you're basically want to treat both of these as point masses. Now, how can we start this? What formula can you think of? So, we have, okay, something is wrong. Okay. So we have U is equal to negative G ME times MM divided by R. So that's going to equal to negative 6.67 times 10 to the negative 11 times 5.97 times 10 to the power of 24 times 7.35 times 10 to the power of 22. And then dividing all of this by 3.8 times 10 to the 8. This is going to be approximately negative 7.7 times 10 to the 28 joules. Now, for the speed of the moon when it collides with the Earth, that's going to be, you have to use energy conservation. And that's basically going to be the absolute value of U is equal to the kinetic energy. So that's going to be 1/2 m of m. V squared is going to equal to G times ME times M times M. Divided by R. So that's going to be 1/2 V squared, and that's going to be G times M times of E divided by R. So then solving for V, taking that. Then you multiply by 2. That cancels out. Then you take the root of both sides. We have that 2GM E divided by R is going to be equal to our velocity. So then solving for our velocity, we have, this is going to be the root of 2 times 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 divided by 3.8 times 10 to the 8. Now, this is going to simplify to approximately 1.45 times 10 to the 3 meters per second. And this is going to be approximately 1.45 kilometers per second. Now, let's talk about what is escape velocity. Well, an object escapes if it can reach or approaches infinity with 0 speed. So basically, at infinity, we have that the initial energy at radius r is going to be E initial is equal to K initial plus U initial. So can I get an initial plus the potential initial? So then the final total energy at infinity is going to be EF is equal to 0. So by using conservation of energy, we have that K initial plus U initial is going to be equal to 0. So continuing with this, we have 1/2 mv squared E is equal minus okay, that was annoying. Negative gm divided by r is equal to 0. 1/2 mve squared is equal to gm r v squared E is equal to 2gm over r. And then VE is just going to equal to the square root of 2gm over r. 1 second. Just need to get some things. Okay. So therefore we have that for mass m orbiting a much larger mass m at radius r, well, we're going to have ug is equal to negative g times m divided by r. So then we have that in a circular orbit, we have that gravity provides the centripetal force. So that means that we can set g times m over r squared equal to mv squared, which is from the first centripetal force. So then after this, we can cancel out m, and we can also cancel out one factor of r. Yeah, that's one factor of r. So then we just get v squared is equal to gm over r. So now after this, we have also that k is equal to 1/2 mv squared. We have ug is equal to negative gm times m over r. So then you get k is equal to 1/2 m times g times m over r. So then you get k is equal to g times m over 2r. And then k is also equal to negative 1/2 of u times g, potential energy of gravity. Now let's also talk about what is Kepler's law. So Kepler's law is based, he has 3 laws, and they're based off the ellipse. Okay, so let's just specifically talk about law 3. A planet's sidereal period, which is basically the same thing as the orbit around the sun squared, is directly proportional to its semi-major axis cubed. So we can draw a diagram of this. So that's going to be, but first p squared is proportional to a cubed. So now we can draw an ellipse, and this is just the ellipse, and then we can split it into its major axis, which is going to be, this is the major axis, and then this is going to be the minor axis, and then this is going to be length A, and this is going to be length E. So then we can draw a right triangle right here. So after we draw this right triangle, we can just put the sun right here. This is going to be the sun. And then this is going to be F. And then we can label this as this is the semi-major axis. It's just semi because it's half of it. And this is also known as the perihelion. And then, well, that's not the perihelion. This is the distance from the sun right here. So this is actually the perihelion right here. This is better representation. And then this is going to be called the aphelion. So some values for this that we can draw out in a table are going to include or follow the format of the sidereal period, P of the year, and then we're going to have the semi-major axis, AU, and then we have P squared is equal to A squared. So, writing some values out for this, we have, for example, we have Mercury, we have Venus, Earth, Mars, and we have Jupiter. So we're going to have 0.24, 0.61, 1.00, 1.88, and 11.86. This is going to be 0.39, 0.72, 1.0, 1.52, 5.20. This is going to be 0.06, 0.37, 1.00, 3.53, and 140.7. And this is going to be the same thing because they're going to be, they're about the same, except for some small differences. And yeah. All right, that's it. Thanks for watching.